Okay, so we're going to talk about normalization today, which is the bottom-up way to do modeling of a database. But before I do that, there was a couple problems I know gave people fits on homework 2, and I meant to go over them on Tuesday and forgot, so I'm going to go over them today. And if you have other questions, please see me after class about it, because it does take sometimes a while to figure out exactly how I did it. It's not like I can just look at these things either and just say, bam, that's how I did it. So it does take always some effort to figure out what to do. So the first one that gave some of you problems was figuring out how to list the details of all rooms at the Grosvenor Hotel, including the name of the guest staying in the room if the room is occupied. So the thing that you kind of needed to do here was realize that you're going to have to probably do a left join. And the reason for that is that it said including the name of the guest staying in the room if the room is occupied. So you kind of, one thought should be is I'm probably going to have this relation, some relation that has rooms in the Grosvenor Hotel. I'm just going to call it Gross Hotel. Ha, gross. Call it Grosvenor Hotel. So it's going to have some rooms like say 100, 200, 300, 400, 500. And so what I'm doing is actually visualizing what the probable endgame is. So on one side, I'm likely to have a relation with the rooms in the Grosvenor Hotel. On the other side, I'm likely to have a relation which also has rooms, but with guests that are occupying them. So also, I'll call it Grosvenor Hotel rooms plus guests. So it might be 100 Mickey Mouse, which I'm just abbreviating with their initials, maybe 300 Snow White, maybe in 400 we have Winnie the Pooh. And I know that's hard to read. I'm sorry. But when you do a left join of these two relations, which remember in relational algebra would look like that with the left end open, you would end up with something that looked like 100 with Mickey Mouse. 200 doesn't have a match in the right-hand one, so it would end up with null. 300 would end up with Snow White. 400 would end up with Winnie the Pooh. And 500 is not in there, so it would end up null. So that's what you want to get to, is two relations, one which has all the rooms in the Grosvenor Hotel and the other which has rooms in the Grosvenor Hotels that are occupied. So the way I went about doing it was I actually created two views, one for the rooms in the Grosvenor Hotel and one called occupied rooms. So getting the rooms in the Grosvenor Hotel was pretty easy. That's just select star from room where the hotel number is equal to the identifying hotel number for the Grosvenor Hotel, which I can get with a subquery by selecting hotel number from hotel where the hotel name equals the Grosvenor Hotel. So that's pretty simple. Getting the right-hand side is a little more complicated. Now I'm going to have to go into the booking relation and find all rooms in the Grosvenor Hotel where the current date is between date from and date to. So now, and also I'm going to have to retrieve the names of the guests occupying that room from the guest relation. So now, the second view is going to be a three-way join among the hotel booking and guest relations. Now, from them, I'm just selecting two attributes, the guest name and the room number. So one of my conditions is definitely going to be that the current date has to be between date from and date to. So that's going to give me the occupied rooms, all occupied rooms. But of course I want to limit the occupied rooms to those in the Grosvenor Hotel. So I want to have, so my join, I joined the booking and hotel relations on the hotel name, restricting the hotels to the Grosvenor Hotel. So I'm only going to be retrieving bookings where I'm going to have people in the Grosvenor Hotel, and then this join of the booking with the guest is going to allow me to retrieve the guest number from the guest relation, and by doing that I'll be able to figure out what the guest name is. So once I have those two views, now it's pretty simple. I simply do my left join. Okay, that's my rooms, that's my occupied rooms, and I'm just matching up on the room number, and here's my left join. Okay, so one thing you have to be careful of here is, just like, I'm going to give you a math example first. So if I have A plus B times X plus Y, okay, that's very different than A plus B times X plus Y. Can someone tell me why the second one is different from the first? That's right, because right here, it's right there. That's the way the compiler is going to interpret the operation. So the same thing holds true when you're doing relational operations. Okay, in getting my two views, what I did, I created one view which was Grosvenor rooms. And I then did a left join of that with occupied rooms. If I didn't have the parentheses, so this was view 1 and this was view 2. So in effect, by creating two views, I was implicitly putting the parentheses around my query like that. So when I saw several of your solutions, when I helped some of you with the solutions, you were doing things like you would get the Grosvenor rooms, but you wouldn't use these, in effect, parentheses. And you were doing it with the occupied rooms. And the problem with not parenthesizing it was that out here you had a where statement that said where current date is between date from and date to. And because you didn't parenthesize it, what happened was it did this join first. So it did it too early. It came up with all rooms in, it actually occupied rooms wasn't occupied. It was some, I can't reproduce it exactly, but it was something where this one was also a select statement from rooms as well, and it was trying to restrict it to the Grosvenor Hotel. And this thing right here was generating a relation that had all the rooms in the Grosvenor Hotel. okay, including the nulls for 200, say, and 500. The problem is that then, because it's now doing it sequentially, this where statement got executed, and it poleaxed the two entries for the unoccupied rooms. And so some of the solutions I was seeing, the queries were generating just the table with occupied rooms. And if they just parenthesized the solutions, so that it should have been parenthesized like this, it would have worked. But because the parentheses weren't in effect in the right place, the left join was getting done too early in the process. The left join needed to be the last operation performed. Instead, because of the way the operations were grouped without using parentheses, the left join was the first operation performed. Later, the filter on the current date mowed down all the, or eliminated all of the unoccupied rooms. So one point, even with SQL, is order of operations is important, and you often have to parenthesize your operations to ensure that they get executed in the right order. It's just like multiplication and division. Okay, so doing your operations, so the queries were often right, or pretty much right, if they had been properly parenthesized. Okay, any questions about that? Okay. So the other one that there was a couple issues with creating double booking and so not having a room double booked and not having a guest double booked. So there's a difference between a room being double booked. That means two guests are trying to stay in the same room at the same time, and a guest double booking, which means a guest trying to stay in two different rooms on the same evening. Also not good. So for rooms not being double booked, what you needed to do was you're kind of wanting to make sure that if you have the same room, let's say these are the two date ranges. So this is date from, date to, from, and to. So this would be a double booking on the room because it has an overlapping pair of dates. So what you essentially had to do is for each room at any hotel, you had to pull every possible pair of bookings for that room and compare the dates on those two bookings and make sure that they don't overlap. And one way to make sure that, well, you couldn't actually directly test for it. Instead, what you wanted to do was pull out all double bookings. So in fact, you wanted to try to retrieve every double booked room and then say that that relation was empty. That's the constraint you wanted to enforce. So to get every pair of bookings, you can actually join a relation with itself. And that's a concept you should get comfortable with, of joining a relation with itself. Okay? That does give you pairs of tuples from the same relation. And sometimes you need pairs of tuples from the same relation. This is one of those cases. And then the check was to make sure, it's kind of, you know, okay, so you can kind of look at it. Here's from, this is a non-overlapping one. So if you were looking at it, you can kind of see that they're basically not, if this is, say, booking 1, and this is booking 2 down here, there's kind of this thing that, okay, if booking 1 dot from is greater than booking 2 dot 2, then there can't be an overlap, right? Because we know that booking 1 is after booking 2. Correct? Okay, so that's one condition that excludes double booking. Or we could have the opposite case, and again, I know it's not too easy to see this, but it could be over here, and we could have booking 2 dot from be greater than booking 1 dot 2. And again, that means booking 2 has to occur after booking 1. So that gives us, that's something that says they're not double booked. Okay? But we were interested in retrieving rooms that were double booked. Okay? So basically we want the not of that, because this condition gives us rooms that are not double booked. So we actually inverted it, and that's what gives me, so if I invert it, okay, and you use De Morgan's law on it, you get book 1 dot from is less than book 2, sorry, yeah, booking 2 dot 2, and booking 2 dot from is less than booking 1 dot 2, which I believe is what I have here. Yes, that's what these two conditions right here. Okay, I know I labeled them A and B. I'm sorry, B and C rather than B1 and B2, but those are those conditions. And then the remaining 3 have to make sure that I'm comparing bookings for the same room at the same hotel, and I'm always going to be getting one pair of bookings for exactly the same room with the same guest. Okay, so let's see, if Sadiqa is booked into room 300 at the Grosvenor Hotel on January 30th, when I do the join, there's going to be one pair where both of her bookings are in that pair. So I have to also exclude the case where the guest numbers are identical, because there is always going to be one pair of bookings where the guest number is identical for that night. And so it boils down to 2 conditions to try to retrieve double booked rooms, and then 3 conditions to make sure that we're actually legitimately a pair of double booked rooms. Namely, we're looking at the same room in the same hotel, and it's not for the same guest. Okay, so that's what gives us, make sure that, well, that whole query gives us the set of tuples for double booked rooms, and then we want to ensure that none of them exist. So the check actually says not exists. So that condition will be true if the relation is empty. Okay, and then for guests not double booked, it's the same general idea down here. We're going to be looking again to make sure that the guests aren't, we're looking for bookings from a guest where the dates overlap and they're in either a different hotel. Okay, so that's one bad thing. They tried to book 2 rooms in different hotels on the same set of days, or they might be in the same hotel and tried to book 2 different rooms. Okay, it's not just a problem if they're in 2 different hotels, it's a problem if I tried to book room 100 and room 400 at the Grosvenor Hotel. So that's why there was 2 conditions there. One, to make sure they didn't try to make a reservation in 2 separate hotels. A second, to make sure they didn't make 2 reservations in the same hotel but in 2 different rooms. And then, of course, again, we have to make sure that it's the same guests trying to pull this on us. So questions about those 2. Those were the biggest, I guess, the questions I got, those were the big ones. David, were there any others, bad things with that you can remember on homework 2?
Get your credit.
Okay, so A, I'm not ready to discuss that one, and B, since it was extra credit, half the class hasn't looked at it. Okay, so, but I'll keep that in mind. Okay, we good? Let's move on in that case. So let's get rid of Firefox. Let's get rid of my 102 exam. Take a quick look. You could probably sell it for some good bucks. And actually, they may be the 2 questions that are getting eliminated from the exam because we may not have gotten that far. You could really, actually, you could have some angry students like Hornets coming after you for selling them the wrong questions. Okay, so I actually gave you a paper copy of the staff-branch relation, and I've uploaded the slides to Blackboard so you can also take a look at them. And we're going to actually be showing you a slide with the functional dependencies, so don't worry about it. You don't need the textbook either. So I gave you the one slide that really matters. Okay, so normalization. I said it's a bottom-up technique for doing database design. And what it's seeking to do is to decompose your relations into logically related sets of attributes. And it's also trying to minimize the amount of storage that's in your database by basically making sure that unless an attribute is a foreign key, it appears in only one relation. So another way to think about normalization is normalization attempts. It's not always successful, but normalization attempts to ensure that each attribute appears in at most one relation, or actually in only one relation, unless it's a foreign key. Okay, so if it were to appear in 2 separate relations and not be a foreign key, then you have an issue with data redundancy, and you may have update problems. And it's also trying to make sure that not just that it appears in only one relation, but that it's grouped with other logically related attributes. So for example, if I have a client number, logically the client's name, their address is going to be grouped with the client. If it's a branch, logically its telephone number, its manager, its address is going to be grouped with it. So it's trying to group attributes together based on what are called functional dependencies. So that's a big thing with normalization, is you're trying to determine which attributes are related to each other. So functional dependencies will be relationships between attributes, and that's how normalization is able to determine that attributes are logically related. And then, like the slide says, it's a bottom-up design technique, whereas entity relationship modeling is top-down. So one thing with normalization is, in the extreme, you would just take all of your attributes from every single form that you can lay your hands on and every single interview, put it in one massive single relation called the universal relation. And then you would figure out the relationships among the attributes and use a series of rules to decompose that one massive universal relation into smaller sets of attributes or into smaller sets of relations. Okay, so as I said, normalization is going to attempt to minimize the likelihood of introducing inconsistent data and minimize the amount of redundancy. Okay, so by reducing redundancy, that's actually minimizing the likelihood of introducing inconsistent data. Because if you have redundancy, whenever you do an update, you have to make sure that you update every duplicate pair of values. And basically, I don't care about this. Basically, the way I tend to design a database is I usually use ER modeling because I like to look at the big picture. And then once I have a set of relations from the top level, then I typically check my relations using normalization to make sure that I've decomposed them in the right way. So I usually use approach 2, which is first do ER modeling, then use normalization to check the structure of my relations. If you're a bottom-up kind of person, then you could just start, like I say, with all the forms and interviews and dump everything into a single universal table and just use normalization. So if you're Mr. Math or Mrs. Math or Ms. Math, that's the way to go. Okay, so I gave you all this picture so that you can look at it as we go along. And actually, I need to look at it too. So here you have a bad relation. It has too much information in it. It has both the staff and the branch put together in one relation. And can someone tell me where there's redundant data here? Surely you can see some redundant data. The branch address. 163 Main Street, Glasgow is there 3 times. 22 Deer Road, London is there twice. So one issue I'm going to have is that if I put a new staff, I hire a new staff member, and I insert them into this relation, then I'm going to have to include not only their branch number, but also the branch address. And should I get it wrong, that's going to be an issue. So that's something called an insertion anomaly. I could, when I do an insertion, actually mess up the database by putting in something that's incorrect. Okay? Another issue is, let's say that the branch's address changes. We got a great new deal, okay, because I'm Mr. Cheapo in the rundown district of London at, say, 100 Rip-Off Lane. And now I have to change all the addresses from 22 Deer Road to 100 Rip-Off Lane. Not good. I may actually forget one of the tuples, and then I'll have inconsistencies in my database. Okay. Another issue is, I know this is unlikely, but suppose that I delete all the staff. Let's say that I delete Mary Howe from this database or from this relation. Do I have any other relations in there for branch B7? No. So now I've lost the information about B7. If I try to do a query that says select branch number and branch address from staff branch, branch 7 won't show up. So that's called a delete anomaly. By deleting Mary Howe, the last staff person at branch B7 from this relation, I lose information about branch 7. So so the delete anomaly causes me to lose information. Okay, so basically that's what I have here. The delete anomaly, if I delete all the staff associated with the branch details get deleted. I already talked about the update anomalies. Okay, here's another issue. Let's say that with insertion, I've created a new branch. Just a second, let's say I've built a new branch, or I'm going to open a new branch, B9 in Paris, but I don't yet have any staff for it. Okay, so I could try to insert a tuple into the staff branch relation, okay, that says B, say 009 Paris, but since there's no staff yet associated with it, I have to put nulls here. You may think, okay, that's not a problem. Why is it? I heard someone whisper it. Primary key can't be null. So staff number is a primary key, it can't be null. So I'm stuck. I actually can't insert my new branch. So that's an insertion anomaly. Okay, yes, Sadika. The delete anomaly. Okay, so the delete anomaly, so here's Mary Howe at branch 7, okay? She's the only staff member at branch 7 right now. Let's say I delete her. I'm not actually closing down branch 7. Maybe I need to renovate branch 7. So maybe I'm just temporarily putting her on leave, or maybe I'm moving her to a different branch. In either case, the information about branch 7 is going to disappear from the database because there's not another entry for branch B7 in the relation.
Are we assuming that there is no relation called branch?
Correct. So normalization, what it's going to do is it's going to decompose this staff branch relation into one relation called staff and one relation called branch. And that's going to solve all these anomalies. So what I'm trying to do is, you could think of this as one of those things where maybe you just designed it and you thought this was a good design for a relation, and I'm showing you why it's not. So you've already seen how if the staff relation and the branch relations are two separate ones, that there's no issue. But I'm pretending we're starting from scratch and we put the two, we put them together. We thought that was a good idea. And I'm showing you why it's not a good idea, how that creates problems. And then I'm going to show you how normalization could actually eliminate this problem. Okay? Okay, so if you're not careful, you're going to get insertion, deletion, and modification anomalies, and that's what we're trying to avoid. And the way we're going to try to, the way we come into that problem is because there's too much information in a single relation. And to get rid of those problems, what we need to do is decompose them. But when we decompose them, we need to make sure that they can be rejoined. So if we break the staff-branch relation into two separate relations, we still need to make sure that if necessary, we could create this view. So we might like to be able to create, this is perhaps a roster. This looks like a roster, right? A directory. So we want to be able to create, say, a view called directory and have it produce a listing that looks like that. And to do that, we would have to do a join on our decomposed relations. So one important property of decomposition is we can't lose any information. It has to be lossless. When we should, by doing a join, be able to reobtain all information that was in the original relation. And then the second thing is that if we had some constraint on the original relation, that constraint is still enforced in the decomposed relation. So for example, the big problem, well, you have it in front of you. The problem that was being caused in staff branch, one of the problems is that the branch number uniquely determines the branch address. Okay, so that's a constraint. The branch number, given a branch number, say B009, it should always map to the same branch address. So if we decompose the staff branch relation into two relations, one of which is a branch relation, we should still have or be able to enforce the constraint that branch number determines branch address. So that's what this second dependency preservation property means. Okay, so to do our decomposition, we have to identify these dependencies among attributes, and they're called functional dependencies in the relational database literature. And a functional dependency is just like a mathematical function. Okay, so you basically, it's denoted as A with a left arrow or an arrow B, but what it's really saying is that given some set of attributes A and a unique set of value or a set of values for them, it uniquely determines some value B. So it's just like a mathematical function. It's saying that the attributes in the set B are uniquely determined by the attributes in A. So for example, F of branch number creates a unique branch address, or F of staff number creates unique salary, name, branch. Sure, I'm missing opposition. So in this case, a single attribute on the left functionally determines a set of attributes on the right. Okay, and again, it's shown in, we denote functional dependencies in this course. We call the left side the determinant, so A is called the determinant, and B is what's being determined. So there, the determinant refers to the attribute or group of attributes on the left side of the arrow. So as an example, should be pretty clear, should all be good with your functions, but staff number uniquely determines someone's position, but if you look at your little relations there, you'll see that a position does not uniquely determine a staff number because, for example, both SL21 and SG5 are both managers. So you couldn't say that position is a determinant of staff number. Okay, and also, it's not enough to look at the data. So it's very easy to look at that table in front of you and conclude that a functional dependency is staff name determines staff number. Because if you look at it, there's not a single duplicated staff name, right, in that relation I gave you. But we know in real life that it's possible we could get a duplicated staff name. We could get two members called John Smith. It's unlikely, but we could even get two John Smiths with the same middle name. So when you are coming up with functional dependencies, you just can't look at your sample data, which is what a lot of people or new designers do. They just look at their sample data and they derive the dependencies without thinking about, is the sample data really capture all the possible data, or is there other potential data that would make this functional dependency not hold? So it really is the case that we try to, well, not try, we're supposed to have unique staff numbers for each staff. But if you'd really dig in, you'd probably realize that you can't guarantee that staff name uniquely determines a staff number. So that's what this slide's all about. Okay. So we have several properties that need to hold for functional dependencies. One is we want the determinants to be the minimal number of attributes necessary for that functional dependency to hold. So we can't remove any attribute from the determinant and still have that functional dependency. So if we have that, we call it a full functional dependency if it's a minimal set. So as an example, and if it's not, we call it a partial dependency. So here we have that a staff number and a staff name uniquely determine a branch number. So if we know someone's staff number and staff name, then we know their branch. Can we remove, well, you can see it. What can we remove from that determinant and still uniquely determine the branch number? Staff name. So if we only keep staff number, we still uniquely determine branch number. So we call the dependency you see there a partial dependency. So partial dependencies are bad. Okay, you want to have full functional dependencies. You'll see that one of the normal forms is one that eliminates partial dependencies from the relation. Okay, so one of the normal forms is going to ensure that we only have full functional dependencies. Okay, and you know that, blah, blah, blah. Okay, the other big thing that we're going to care about is transitive dependencies. So sometimes we'll have A determines B, B determines C, which means through a transitive dependency that A determines C. Okay, and a good example of a transitive functional dependency is we know that staff number uniquely determines a person's name, position, salary, and branch. We also know that a branch number uniquely determines a branch address. Therefore, we have a transitive dependency that staff number determines branch address. Now, that's not one that you would normally come up with, right? You don't normally think of the staff numbers uniquely determining the branch address. You think of the staff number as determining the branch, and then the branch determines the address. So it's a transitive dependency. It's not one that you explicitly represent. It's an implicit dependency. Okay, so a transitive dependency is an implicit dependency. Okay, derived from explicit dependencies. Okay, so if we try to identify a set of full functional dependencies for the staff-branch relationship, this is what we might come up with. So you're probably pretty confident about the first two because we've already discussed them. It's almost certain, I mean, generally addresses uniquely determine our branches. Okay, if we have enough information, 22 Deer Lane, maybe it would require a city and a zip code, but I certainly can get to the point where if I have enough information in the address, it's going to uniquely determine a branch number. Then the other ones you may not get just by looking at the data, and that's why you have to have interviews. So someone might tell you that the branch number and the position determine the salary. So we might pay someone in our Paris office more than someone in our office, I don't know, in Glasgow, Scotland. Maybe Paris is a more expensive city, so we have to pay our people more, whatever. But it might come out either in the interviews, or you might figure out by looking at the data and then confirming that the branch number plus the position determines the salary, and then similarly that the branch address and the position determine a salary. Okay, and this one is, you could easily derive it from this and this. So 1 and 2 imply 3, right? Because branch number determines branch address, so therefore you could replace in 2, you could replace branch number with branch address and get the same thing. I'm sorry, no, I messed that up. Opposite. Sorry. Actually, this one. So 1 and 2. Since you know that the branch address uniquely determines the branch number, you know that you could substitute this in here, and that yields 3. Okay, so at any rate, once you have your functional dependencies, now you're ready to go on to step number 2, and that is to identify your keys. Okay, so again, keys need to uniquely identify all attributes in a relation. Now here, and it doesn't necessarily, you may not find a dependency, one dependency that uniquely determines all attributes. So here, this one comes close, but what's it missing from the staff-branch relation? There's a missing attribute. We'd like to say that staff number is a primary key, but that doesn't give it to us. Why not? There's a missing attribute. You're missing branch address. Okay? However, we see that branch number uniquely determines branch address. And since branch number is there, we can kind of through transitivity get to the fact that the staff number determines everything. Sometimes it's going to turn out, let's go forward. Come on a lot, it looks like. There we go. Sometimes your primary key does not determine, so you're going to have to do more than that. It's not going to get it just through transitive relationships. So in this one, we have what I call a client rental relation. So we are showing the client, the property that they're renting, their name, the property's address, when the lease starts and finishes, the rent they're paying, and who owns the property. So here it turns out that client number and property number is the primary key. But if you just look at client number and property number by themselves, they only uniquely determine 2 fields, the start and finish dates for the lease. So if you know the client and the property, you know when the lease started and finished. Now, I'm assuming the same client doesn't rent the property twice. But you can then use you can use partial dependencies to derive the rest of the attributes. So, client number and property number, when paired, determine only two of the attributes. But client number by itself determines client name, and property number by itself determines the rest. So we get these two from the pair, we get this one from client number, and we get these four from property number. So by then looking at the partial dependencies that we get from subsets of the primary key, we may be also able to derive the remaining attributes in our relation. So it's not always transitive dependencies that allow us to get the rest of the attributes. Sometimes it's partial dependencies that allow us to get them. So now I have to go way back in my presentation. Okay, so we've kind of already talked about identifying primary keys and candidate keys, so I'm going to gloss over that and now get to how we use functional dependencies for doing normalization. Okay, so it's actually there's a whole series of normal forms, and we're only going to go up through third normal form. You can get all the way up to, researchers have come up with a whole set of higher normal forms. B, C, and F stands for Boyce-Codd. In my opinion, it's a diminishing marginal return. So if you're looking at the benefits of normal forms on a scale, so first normal form, second normal form, third normal form, fourth normal form, Boyce-Codd normal form, fourth normal form, blah, 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 versus benefits, it's what's called diminishing marginal return. So they tend to be very high initially and then they level off. And they basically level off pretty steeply, in my opinion, after third normal form. And not only do they level off, but higher forms like Boyce-Codd normal form, in my opinion, are much less intuitive and harder to understand. Plus, as you move up into those higher normal forms, you're actually sometimes reintroducing data redundancy. So in each step, each normal form is supposed to eliminate some kind of data redundancy. The problem is once you get above third normal form, I believe that every normal form above third normal form potentially introduces some form of data redundancy while eliminating some other form. Up through third normal form, you're strictly reducing data redundancy. So in my opinion, that's another good reason for normally stopping at third normal form. And it's almost always good enough. So the book actually talks about unnormalized form. I would not worry about it. By unnormalized form, they mean you may have columns with repeating attributes. So remember, one requirement of the relational model is you can't have multi-valued attributes. So the book calls unnormalized form a table that could have multi-valued attributes. And the way that you essentially then get it into first normal form says that every attribute is single valued. That's what that definition says. Every attribute is single valued. Okay, so if you want to get from unnormalized normal form to first normal form, you have to eliminate your multi-valued attributes. Okay, this method stinks. Okay, don't use it. So it might be the case that you have at most 3 phone numbers. So maybe you can bound the potential number of values that you have for an attribute. And in that case, you could create a column with that, or you could create that number of columns. This just creates a nightmare when you're trying to write your queries. Now, in order to retrieve, say, the phone numbers, you have to say select, and now what are you going to do? You're going to say select, well, phone number 1, phone number 2, phone number 3 from, say branch. Well, that's not necessarily, okay, maybe that is okay for you, but that's, pardon?
Still missing, you gotta eliminate the nulls.
That's, well, you just may have nulls showing up.
Have nulls showing up.
Right. So you may be okay. Yeah, so Ryan's point is you actually may end up with a number here, but a null here and a null here. And he said you have to eliminate. And I said, well, maybe and maybe not, but it's certainly not pleasant. But let's also say, just a second, John, let's say I want to ask a query that says select all branches who have 2 or more phone numbers. Good luck. Okay, you can formulate the query, but it's not going to be pleasant. And I can just keep coming up with examples of queries you may want to ask that are going to be a pain in the neck to answer if you put it out like that. Whereas if you use number 2, where you put the repeating data into a separate relation, it works great. So the book says either or. I will hold my nose if you try to use the first way. Okay, so I would want you to put that repeating information into a table, so you'd use branch number as the primary key and then the telephone number, and that way you also aren't having, well, that's not true. I was going to say you're not losing, you're not wasting space, but in fact having the branch number here is an extra use of space. So you may actually be taking up more space, or you may be saving space depending on how sparse this table is. John, you had a question.
I think I figured it out.
Okay.
It was about the ordering of the development.
That could be a problem too. Okay. It's a problem. When I first started doing databases, and this was about 20 years ago, no, I started in my PhD program. I actually switched, and I used to think it was better to do it the first way, and I quickly got disabused. Okay, so getting to second normal form is we're trying to get to, second normal form says there's no partial dependencies. You only have full functional dependencies among the attributes in second normal form. So if you have a partial dependency, you're going to move that, you're going to remove those attributes from the relation and move those attributes off to a separate relation. Okay, so here again is a relationship where I'm going to have partial dependency. So if you have a sorry, I lost my train of thought. If you have a relation whose primary key consists of a single attribute, it's already in second normal form. Okay, so going back for a moment. So basically, it says every non-primary key attribute is fully functionally dependent on the primary key. Okay, that means that by that definition, that every relation whose primary key is a single attribute is in second normal form. Can someone tell me why that is guaranteed if it has only a single attribute? This would be a great homework question. So second normal form says no partial dependencies, right? That's what I just said, no partial dependencies. So if you have a single attribute, how can you possibly have a partial dependency? Okay, remember partial dependencies occur when you have two or more attributes and one of the attributes can be removed from the left-hand side of the determinant. So if you have a single attribute on the left-hand side of the determinant, you obviously can't reduce it to 0, so you can't have any partial dependencies. Partial dependencies only can occur when your primary key has two or more attributes. So here's a good example. I can't use the staff branch relation for exactly that reason. The staff branch relation has a primary key that's a single attribute, so I had to pick this one instead. So here we're basically keeping track of our leases. Think of this as a lease, okay, which is perfectly reasonable that you might originally organize it like this, because a lease probably has all this information on it. If you took it off the lease form, there's a chance that all this information will be on that lease form. So there's a good chance that if you were designing, even with entity relationship modeling, there's a good chance that you would just yank all the information off the lease agreement and create this relation. But it's not in second normal form. Okay, and here's why. If you look, here are two partial dependencies. So client number uniquely determines client name. So I don't need the property number to determine the client name. I only need the client number. And here, the property number uniquely determines the property's address, its rent, the owner's number, and the owner's name. I don't need to know anything about the client in order to know what the rent on the property is. The rent is what the owner says I want. I want $1,000 for my property, okay? That's what you're going to get. Doesn't matter who the client is. The owner number, the client, whoever rents it, doesn't cause the owner number to change. That's associated with the property. So is the owner name. So those are partial dependencies. And then there's two candidate keys, which we chose not to use here. I'll get back to that in a moment. But the way that we decompose this relation into subrelations is we remove each set of attributes that are associated with a primary, we remove from the relation, let's do it again. For each partial dependency, we create a new relation. That new relation contains all the attributes in the partial dependency. So we're going to create two new relations. One is going to be a relation that has client number and client name. And we're going to create a second relation that has property number, property address, and I'm going to abbreviate, rent, owner number, and owner name. So we're going to create two new relations one for each partial dependency, and it's going to contain all the attributes in that partial dependency. So that's step one. Step two is we're going to remove from the original relation all the attributes on the right-hand side of the partial dependency. So the attributes on the left-hand side are going to stay. They're part of the primary key. Okay, your partial dependencies are coming from the primary key. So the attributes on the left-hand side of the determinant, they stay in the original relation. The attributes on the right-hand side get eliminated from the original relation. So when we're done, the original relation is still going to contain client number and property number. Okay, but this will be gone, this will be gone, this, and this, because they're all part of the partial dependencies, and all that will be left is rent start and rent finish, which is a full functional dependency, right? The full functional dependency was on rent start and rent finish. So when I'm done, those three relations are in second normal form. So does that make sense? So step one, move the all the attributes in a partial dependency to its own relation. Step two, remove the right-hand side attributes from the original relation. That, when you're done, will give you, in this case, three relations, all of which only have full functional dependencies on the primary key. Okay? And remember that lossless join property? We said when the decomposition occurs, it has to be rejoined. The fact that we kept the determinant, the left-hand side attributes, in both the original relation and the new relation is what preserves the lossless join property, because we can join on that common set of attributes. So when we moved property number and retained it also in what I'm now calling the rental relation, okay, I can still do my join and reclaim most of the original relation. Same thing with client number. By keeping the client number in the rental relation, if necessary, I can join it with the rental relation to regain that information. So by keeping the left-hand sides, the determinants, in both the original relation and the new relation, I preserve the lossless join property. Make sense? So basically, the determinant becomes the foreign key. So, see, I bet that's not on any of my slides. Nope. So, by retaining the determinant, in both the new and the original relation, we preserve the lossless join property. And two, the determinant becomes a foreign key, in the new relation. Because that's what a foreign key is, what we join on. Okay, if you go back here, and I get rid of all my stuff, whoops. So notice we've also how we're eliminating redundant information. If we had multiple over time, as we get multiple clients leasing the same property, we would be duplicating the property address, the rent, the owner number, and the owner name, assuming the rent doesn't go up. We would be duplicating that information. By moving that information off into its own relation, we're no longer going to duplicate that information. Now there'll be only one record for each property. And we won't be duplicating the property address, the owner's name, the owner's number, etc. Now, you might be sitting there thinking that's not exactly right, because if you look at this one, what's being duplicated? There is something being duplicated there. What's the duplication? Yes, if an owner has more than one property, we're duplicating the owner name. So the problem is there's a transitive dependency lurking here. Okay, the owner number uniquely determines the owner name. So we have a transitive dependency, and third normal form gets rid of transitive dependencies. So third normal form is a relation that is in first and second normal form, and in which no primary key attribute is transitively dependent on the primary key. So when you're doing your normal forms, every higher normal form says you're in the lower normal forms and some additional constraint holds. So in third normal form, you're in both first and second normal form, and there's no transitive dependency. So how do we move from second normal form to third normal form? We find all our transitive dependencies. For each transitive dependency we find, we move all the attributes in that transitive dependency to a new relation. Then the right-hand side, we delete those attributes from the original relation. The left-hand side, which is the determinant, stays in both the original relation and the new relation. And that's what preserves the lossless join property. So it's the same technique that you used for going from first to second normal form. So to get into second normal form, you eliminate partial dependencies. To get into third normal form, you eliminate transitive dependencies. So here, to get into third normal form, we move these two off into their own relation. And because owner number is the determinant, it's going to occur both in the old and new relations. So when we're done, we now have an owner relation that has owner number and owner name, and property for rent now only has owner number in it. If we really need to get that information back, we just do a join on the owner number and we get it back. Okay, and now everything is in third normal form. Okay, so just one last thing. Everything I talked about today was assuming that the normal form was being done on the primary key. So we were only concerned with partial dependencies on the primary key and with transitive dependencies on the primary key. A more general definition of second and third normal form is that you eliminate, in second normal form, you eliminate all partial dependencies on any candidate key, not just the primary. And in third normal form, you eliminate all transitive dependencies, not just on the primary key, but on any candidate key. So we'll get into that briefly on next Tuesday, but also next Tuesday we're going to go over a case study. Okay, so same thing next Tuesday. I'll probably over the weekend put the case study up, but we'll go over a case study next Tuesday. And then Thursday of next week we'll go over physical database design, and in a week and a half, a week from Tuesday, we have our test over the database part of the course. So, and I'll have homework 4 up probably tomorrow morning. I don't think I'm going to have it up this evening.